Hey, welcome back, guys. Today, we're going to look at standard state in terms of what we call standard enthalpy of formation. Now, this is still part of Hess's law. It is. Okay, so let's review a little bit in terms of what Hess's law was all about. There's some reactions that are just too hard to do in one step. Okay, it's not easy to get the initial and final temperature using a calorimeter. So some reaction, well actually most reaction, are able to be done through stepwise reaction. Okay? And the sum of the enthalpy of the stepwise reaction is equal to the overall enthalpy of the reaction itself. And we looked at a whole bunch of examples yesterday where we had a whole bunch of reactions. So let's go back to this one, like in example 5. Hopefully you've done it. You checked your answer and your answer is right. So there's 3 reactions here, each with its own delta H. Now these numbers, I will show you very soon where you can find them. Okay, but we all know that you can use a calorimeter and easily discover them on your own. But hey, there's so many equations out there, and there are some of them that are pretty hard to do. Why don't we just look them up like we're going to do today? But let's say you did an experiment, you did 3 experiments, and you got these delta H's respectively, but the overall reaction that you really want to do is this one. Okay, so what you can do, of course, is you can manipulate these 3 equations to make it look like this, okay, by following a few simple set of rules. Like if you were to flip this reaction around, you have to make sure you multiply this by -1. If you were to add coefficient, okay, to a reaction, like, I don't know, you might want to multiply this by 2, okay, and you will have to certainly multiply this by 2. And again, later on at the very end, things are identical on the left and right side of the chemical equation. You can easily just cross out. So we've learned that. Hopefully you guys are okay and really find it fun. I mean, who would find it fun? But you don't know. Somebody might. So today we're going to look at standard state. Again, now we talked about this before. Okay, most of these reactions, okay, that are done for you, and the data is in a handbook, are done in what we call standard state. And that's nothing more than 1 atmospheric pressure and 298 Kelvin, which is really 25 degrees Celsius. And for pressure right here, this is really 100 kilopascal. If these are the units that you guys are more used to. And because of that, it wouldn't be just delta H. No, it'll be delta H naught. There's a little degree sign at the top, usually has a slash, but it really doesn't matter. But that's called standard enthalpy. Okay? Because you're going to be going through data in a data bank. And all of these numbers that are presented are experiments that was done by somebody, I guess. And they reported this data based on doing the experiment under 25 degrees Celsius and 100 kPa worth of pressure. Okay. With that in mind, you can actually calculate delta H in terms of the formation of a particular chemical. Now, we'll see what that means later. Okay, but let me just show you very quickly that in your IB data booklet, it is section 12. Okay, so for section 12, your IB data booklet, you can see a whole bunch of chemicals. Now, most of them are organic chemicals. There are, of course, water at different state. Believe it or not, water at different state actually have different enthalpy. Okay, we see, variation of carbon oxides. Okay, and some hydrogen bonded with some sort of halogen in some sort of gas. Now, these are all numbers based on what we call delta H naught of formation. Okay, these are the enthalpy that is required to synthesize one of these. You can even say that methane in a gas state is worth this much to make. And obviously it's worth this much to break. All right, now we'll see how we're going to be using this in a sec, but that is just to give you sort of like a definition of what these things are all about. Right? So I have a little note right here that the more negative the value, meaning the more exothermic the value, the greater the stability of the compound, because nature favors exothermic rather than endothermic. All right. Now, you'll notice that there are some elements that are not in this page. Like, for example, you won't be able to find oxygen gas. You can look all you want. Okay, you can look on the internet all you want. You'll notice that, hey, where's oxygen gas? Oh, where's hydrogen gas? Nitrogen gas? Where are those? Well, this is very important. Okay, so some elements with more than one form, okay, under standard condition, has to be expressed under what we call the most stable form. Like for example, oxygen. Oxygen can be O2. We know that. That's popular. Or it could be O3. Both of these are oxygen that can exist at standard condition. But it is the most stable that is being indicated. And just keep this in mind. These stable elements will have a delta H of 0. They're neither exothermic or endothermic. They just don't have any energy per mole. Something to keep in mind. H2 is the same. Okay, so whenever you see H2, that will also have an enthalpy of 0. Okay. Same with carbon. Carbon can exist as graphite or diamond. Okay? Day 2 would be 0. Right? Just again, something to keep in mind, that the formation of these elements is 0. And here's the formula to calculate the overall delta H naught of reaction. Okay, so the enthalpy of reaction for any reaction under standard state can be calculated by the sum of the enthalpy of the product minus the sum of the enthalpy of the reactants. Now, keep in mind, these chemical reactions must be balanced. The reason is because their coefficient comes into play when you're doing your mathematical work. Now, it only makes sense that we start doing some of these mathematical work as a great way to practice using this equation. So let's go. Oh, here's another sheet right here that I got from the internet. Okay, showing you some other delta HF, okay, that you don't have in your IB booklet. All right, let's take a look at the next example, example 6. I want to find out what is the enthalpy of reaction at your in standard condition. Remember, this is actually very important, okay? Because if this wasn't indicated, you really can't use these numbers because it wouldn't make sense, because these numbers are only based on standard condition. So only at standard condition where you can use those numbers given in a CRC handbook or the IB data booklet, and etc. So I want to know this reaction. What is the overall delta H of reaction? Okay. Now, you're not going to use the colorimeter to find this out, are you? Of course not. Why wouldn't you? 2 reasons. One, you're not going to you're not going to get a hold of this, that's for sure. Second reason, it's a standard condition. Look it up, right? So let's apply this equation right here. Let me write that down. So delta H naught of reaction, sometimes let's just go R zip Rxn, is equal to the sum of the molar times enthalpy of reactants minus, reactant, what am I talking about? Products. You'll see another equation that will be reactants. To the sum of the molar change in enthalpy of reactants. So that's the equation. Now let's find out what these numbers are and let's plug some things in. All right, so delta H naught R is equal to, let's have a big open bracket and let's take a look at the product. So here's the product. Just make sure that the reaction itself is all balanced, because if it's not, you're gonna have to do that because remember, coefficient play a role, they're right there. So let's take a look at this. Look at the product. This is the product, okay? And it looks like it's a 1 molar. So 1 mole. And what is the delta H of formation of this? Okay, what is the change in enthalpy to make one of these? Well, let's go to our data booklet. What was it again? C2H5Cl? C2H5Cl is right there. Okay, so to make this, delta H of formation is negative 137. Let's write that down. Negative 137. Well, it looks like that's the only product, so you don't have to add anything else. So let's close this bracket. Minus, open bracket again. This time, we're looking at the reactants, and whoa, we have 2 reactants. Okay, so you're going to have to sum the 2 up. So let's take a look at the first one, which is this one. Again, this is 1 molar, so therefore 1 times, what is the delta H of this? Oh, let's take a look. C2H4, right? C2H4 is up here. I'm glad they kind of put this in order. And that's 52. Positive 52. So making C2H4 will require 52 kilojoules. Okay, I really should put the units in, but you think you guys can put it in yourself. Plus, because this is a sum of, there's 2 reactants in this case. So HCl, again, this is 1 molar, that's 1. And let's take a look at the enthalpy of formation for HCl. So by forming HCl, should be all the way down here. It releases 92.3 kilojoules of energy. Make sure your sign is right. Okay, that's it. No more reactants. So make sure you do this right mathematically, and you should get an overall 96.7 kilojoules. Okay, worth of energy. So this reaction right here, is an exothermic reaction, with a yield of negative 96.7 kilojoules worth of energy. Okay. Chemistry is a very cool thing. In order for a reaction to occur, bonds here and here has to break apart. To make something, you have to put these bonds back together in a different orientation to make your products. So you know the formation of this, and the formation of this, you can plug these numbers in along with their coefficient and know, more like this. Okay? plug these numbers into their coefficient and be able to find the overall number. Okay? Not just the overall number, but then the overall sign too. If this reaction is going to be exothermic, or if this reaction requires an input of energy. It's pretty cool to think about. Okay? God bless the fact that people made these charts so therefore life can be so much easier as a scientist. Or else you're going to have to find these numbers by doing these experiments. That's going to be hard. Okay? It's actually not easy. It's actually very easy in this case where they give you a reaction. You just have to look up their formation and be able to find if they're going to be exothermic or endothermic and how much. It's really much more easier than looking at a reaction and break them apart and find out their individual delta H. But sometimes we just have to do this because wherever we're working at may not be a standard state. Okay, so if we were to do this reaction right here, okay, and where we are at is not as standard state, you'll notice that your number will be off from this. And you're thinking to yourself, hey, I did everything right. Well, that's because where you're at, your condition is not the same as the condition that where these data are gathered from. I hope you understand. Okay? Sometimes it's not you. Maybe it is. Who knows? All right, let's do another example. And then I'll have some examples that you guys can do on your own. So let's take a look at this. This is a combustion reaction. How nice is that? Definitely not something you want to put in a colorimeter, right? Well, if you want to know if this combustion reaction is exothermic or not, I can tell you it is. All combustion reaction is. Well, how violent would it be if I were to combust this reaction? I know I'm going to release lots of energy, but is it going to be so much that I probably don't want to do it in my basement? This is called benzene. What I'm doing right here is combusting benzene to make 12 mole of carbon dioxide, 6 mole of water, and probably a vast amount of energy to go with that. So let's calculate delta H. All right, I'm not going to write the formula. I hope you know what the formula is. Sometimes I like to do this. I like to look up all the numbers first. So let's look up all the numbers. So let's go here. First, I have C6H6, benzene. All right, right here. Right there. To make benzene, making benzene will require 49 kilojoules of energy endothermically. Oxygen, now, don't let me tell you twice. We know what oxygen is. Oh, we know what oxygen is. You can keep looking at this page and you'll never find it, but you know what it is. You know. All right, carbon dioxide. Yeah, right there. Okay. This is an exothermic thingy with a negative 393.5. Water as a liquid. Be careful here, eh? There's two water. Water is a steam and water is a liquid. The numbers are close, but they're not identical. So make sure you put the right one. There you go. Okay. What I usually like to do is just kind of write them down here. So this is 49. This is negative 393.5. And this is negative 285.8. Okay. All right. Remember I just mentioned the fact that all combustion reaction are going to be exothermic? Look at these numbers. And they're negative. Look at this number. pretty obvious. But I want to know how much. I just want to know how violent this thing is. So let's go. Okay, open bracket. So I have carbon dioxide. I have 12 moles of that at negative 393.5. Plus, well, I have 6 mole of water. And each water is worth negative 285.8. Close this bracket. Minus, I have 2 moles of benzene, and each benzene is worth 49 kilojoules per mole. Plus, I have 15 oxygen, and oxygen is worthless. Close your bracket. Okay, well, I have a calculator on hand. This is going to give me negative 6,535 kilojoules. Man, that's crazy. That's a lot. That's pretty violent. Okay, so don't go around and start combusting benzene now. So this negative 6,535 kilojoules of energy. Now, remember the definitions. It's very important that you understand this number. Not just say, that's the number. Well, you don't understand this number. When you're combusting benzene, it doesn't yield this amount. It yields this amount for every 2 moles of benzene. Let's write that down. It's very important that you write this down. That negative 635 kilojoules of energy was released for every 2 moles of benzene. So it's not like each benzene is going to yield that much. No, it's every 2 benzene is worth that much. Combusted. So if I want to find out what about 1 benzene, how much will combust 1 benzene worth? Well, that's pretty simple. Just take this number and divide it by 2 moles, and you'll have kilojoules per mole. And that will be negative 3,267.5 kilojoules per mole of benzene. Okay? So, hopefully you're comfortable with the language, comfortable with the math. Okay? Don't just know the math without really understanding exactly what's going on. I'm going to leave this one with you. Okay? I want you to do delta HR for the combustion of hydrogen and the combustion of methane. Okay? So I want you to combust those two. So in case you don't know, this is the combustion of hydrogen gas. And this is the combustion of methane. I even balanced it for you. So what I want you to do is I want you to find the delta H of reaction for 1 mole of H2. Okay, I want you to find delta H of reaction for 1 mole of CH4 and compare the 2 numbers. Which one actually yield more energy? I'm sure you guys are okay with that. And yeah, try to do that yourself. Anyway, let's move on. There are other ways of finding delta H. Okay? Speaking of combustion, combustion is probably one of the more popular reaction of all, especially when you're working with hydrocarbons. Now, we all know what hydrocarbon is when we do organic chemistry, because organic chemistry is an example, or organic chemical, or hydrocarbon is an example of organic chemical. Okay, I was a little confused myself there. And because of that, a lot of scientists do a lot of combustion reaction on these organic chemicals. Here in your IB booklet, chapter 13, we have enthalpy of combustion. That's pretty cool. Enthalpy of combustion. Now, what's the whole idea of this? These numbers, okay, are the overall delta H naught for the combustion of whatever you're combusting. So in this case, this kind of gives you the answer for the previous example, example 9. So you can check your answer here. So if you're combusting H2, you're reacting H2 with oxygen gas. What you should yield is negative 286 kilojoules per every mole of H2. As I said, I sort of just gave you the answer for this. But I don't want you to look at the answer. I want you to do this answer and see if it matches with this number. Oh, what am I doing? See if it matches with that number. Okay, this number right here. So what was the other one? Methane, CH4. So if you combust CH4, you would get this number. Okay, so this is the answer for this. Again, I want you to actually do this, not just look at that page and say, oh, I can just look at section 13 and I got this number. I'm not going to do any work, but then this is worth 7. Oh, no. Okay. Just a great way to know certain things, because combustion reaction is definitely very popular. It's very useful. So scientists have discovered the fact, why don't I combust a whole bunch of things, record their enthalpy, right? Record their enthalpy of combustion. So later on, people can use this data. Use this data on what? On these type of questions. These type of questions are based on things that are combustible. This guy is combustible, this is combustible, and this is combustible. If I were to react two combustible elements together to form another combustible element, I can actually use these combustible value or combustion value to find out what delta H is. I don't need a colorimeter to risk my life to do this reaction. I don't really need to look at formation either. I can, but I don't have to. I can look at the results in combustion data. But, if you were to use combustion data to do this, you will need to change your equation to have your reactant minus the product. So let's do question 9. Calculate the enthalpy change for this reaction based on enthalpy of combustion. So not based on enthalpy of formation. I don't want to do this through the formation of this, and this. I want to do this by knowing the combustion of this, and this, because I know for a fact that all three of these are combustible elements. So let's do that. So delta H naught, in this case, is a combustion thing. So I wouldn't even say that because we're just using it. Take this away. Okay, is equal to, again, remember, it's reactant this time. So it'll be 1 mole of, this thing is called ethene. If you look back, it's negative 1,411. Okay, plus 1 H2. Now this H2 is not 0. Okay, you're not looking at formation here. You're looking at combustion, and combusting H2 do give you something. Minus 1, okay, times negative 1,561. There you go. That was ethane's enthalpy of combustion. This is going to give me negative 136 kilojoules. That means it takes negative 136 kilojoules per every mole of this and every mole of this. All right? That's how you would use, delta HC. Okay. I have example 10 here. Okay? And I want you to do example 10, example 11, and example 12. Example 12 is interesting. You're graphing this. This is sort of a way to see if you understand the whole nature of thermodynamics. Okay, and we'll take it up. Okay, question 11. Oh, this is a good question. This question, you're looking for delta T. Remember MC delta T? You're looking for delta T for what's happening right here. This question is everything that we've learned from the beginning when we started thermodynamics. So see if you can do that. Question 10, okay? You will do this reaction based on enthalpy of combustion data. Then you're going to prove your answer. Prove your answer by doing a multi-step Hess's law. Now you may be thinking, how am I going to do that? It's pretty simple. I'll kind of start you off, okay? You probably know how to do this already. So let me show you how to do this same question, but using multi-step reaction. First, you have to understand that all three of these are combustible. So let's combust them then. C plus O2 is CO2. You need to find out what is the combustion for this number is. You can find it right here. Okay, so you're just going to have to find carbon. There you go. Okay. H2. Well, combust this, you get H2O. Now, I'm not going to balance these things for you. Okay, I hope you can balance them yourself. Actually, yeah, I'll balance it for you. There you go. Okay. And C2H6. Actually, you know what? Never mind. I'm not going to balance. I'm not supposed to balance them. Don't balance them. Okay? Don't balance them. Or else the number that you see right here has to be changed. You see how water right here, H2 is negative 286. If you balance this, like if you put a 2 here, it won't be 286. It'll be different. Okay, so in order to use negative 286, don't balance it. All right, so for this one, you have, well, not balance it, but make sure there's no number here. Make sure this is always 1. Okay, just like with this, I want to make sure that this is 1 for me to use the delta H on section 13. So here we go. What would this one be? Okay. With these, you can use your Hess's law from last class and figure out what the delta H for this reaction. C, by doing this, will give you the same number as doing, this. Okay, so I kind of start you off. So remember, when you're asked to do something like this, okay, to prove your answer, combust these guys individually. Okay, make sure all the reaction will have your combustible element as 1. So I guess if you do that, there are times where you're going to have to use fractions. And make this your target and try to rearrange these to become like this. And then sum up all the delta H. See if you get the same number. All right? All right, so I guess I'll stop here. You guys can certainly try to do all of these, and we'll take it up the next day. All right, bye guys.